Another example of using Ampere's law with a little more substance to it is one where we have a thick wire that has a uniform current density. So I want to look at this situation now where I don't have a line, just a thin wire result like the previous, but I want to consider a thick wire. Again, cylindrical in shape. I'll assume it's infinitely long. The radius of it, of the cylinder-shaped wire, is A, and I've got current coming through all of the solid portion of the wire. In fact, we'll assume it has uniform current density. And remember, current density is I per area. And if it's uniform, then that's a constant. So I've got a constant steady current going through this constant area. And if you like, you can call that J naught. The current density is J, and so you use a naught here to indicate that it's a constant current. But one can compute that given the total current I going through it, and the total area then is just pi a squared, the area of a circle of radius A. And the total current going through it, if you were given J naught, would just be J naught times that area, just multiply through that. Well, again, I'll look at it from the top down. So looking at it from the top. And now that I've got the current distributed all over the interior of this wire uniformly. Center of the wire. If you look at all of this current, it's cylindrically symmetric. And so about the center of the wire, the magnetic field has to swirl about it in this fashion. So here I've got one. Inside the wire, it's the same way. It swirls about it in this circuitous fashion. And there's two regions that we need to consider separately. I can choose C1 that's outside the wire with the same center, a circle of radius R. And that has one form that we'll see. And then, alternatively, I can choose another circle, C2, in which it's also centered at the center, going around it in this fashion here. But it is a little bit different in that R is less than A, so it's a smaller circle that doesn't include all the current. Okay? So let's do the outside first, because it's really exactly the same as the case of a thin wire. So now I'm looking at R greater than A. The integral of B dot dl is mu naught I cutting S1 of C. And if you look at this, the area enclosed by the wire, or enclosed by the curve C, is this total area inside, and only part of it's got current going through it, but when I add up all of the current, infinitesimal currents of the J going out of the page at me, I get the total current. Again, this side over here is exactly like that, the case of the thin wire. It just becomes a B by the symmetry as a function of R at best. And then I integrate all the way around as 2 pi R of dl. And mu naught, and then since all the current is cutting, it reduces to exactly the same expression for R greater than A as if I had all the current going through a thin wire right at the center here. So no way to distinguish a thick wire and a thin wire by just measuring the field outside. However, for C2, that's this one inside, it's a different situation because now R is less than A. The left-hand side is the same as the previous problem, and it always becomes in these cylindrical cases, the B is a function of the radius times 2 pi R is this interval. Mu naught, I have to get the total current cutting S2 of C2. Okay? So this is the curve C2, this small circle. I only and want the current that's cutting through the inside of that. These other pieces of current in this annular region here, they're outside the circuit. They do not cut through the area enclosed, and so I don't count these. Well, how would you compute those? Well, in general, you can rearrange this expression to get I as J naught times the area that it's going through. And in our case, we can write this as J naught times the area 2, where area 2 is the area that those currents are going through. That's only the part that's inside. I don't count the ones outside. Well, the radius of that interior one is radius r, so this has a radius r. And so if r is the radius of curve C2, then pi r squared times J naught is the total current that's going through that. It's the current density times the area that it passes through, pi little r squared. Notice I can divide through by r, but it's the same r in both cases. On these, it's the radius of that small circle. J naught, pi r squared. The pi's will go out. Well, what I would probably do is keep those. Let me just go ahead and keep those and plug in what J naught is. Well, J naught, it's just a constant that was I total current divided by going through the total area, which is pi a squared. So for J naught here, I substitute in for J naught, I substitute in I pi a squared into this expression. And now then I can start canceling things. This pi will cancel that one. I have an r here that will cancel this square up here. And then I would write this usually as mu naught I, 2 pi, and I take one of these a's and put it underneath here, and one underneath this r. And so the magnetic field, if r is between 0 and a, is this expression. It's in the theta hat direction, if you want to put in the vector. And it looks like the thin wire outside, so I get a piecewise magnetic field. You can graph that, at least the radial portion of it. For outside, for r bigger than a, it's going to be this expression, so it'll fall off like mu naught over 2 pi r. For inside, if you look at the inside solution radially, it goes linearly with r, so it's just going to be a straight line. I know that at r equal to 0, it's 0, so that's included there. At r equal to a, it turns out that both of these, whether this one or the exterior one, they both get the same value up here, which is mu naught I over 2 pi a. So this maximum value is mu naught I 2 pi a at a. It's linearly upward to that on the interior, so it increases, the magnetic field increases as you go out radially until you get to A, and then it falls off like 1 over r.